So, I mean, I'm really pleased to see so many people here. I'm very, very happy with this. Thank you for coming. Thank you for taking the time to learn about, well, something that I think is really going to have a major impact on the face of statistics in the future. I think that what Peter has been working on is really incredible, is really beautiful, and I think it's really going to change everything. So this is like an early opportunity to get a peek of what the future of statistics is like. But this is not the first time that Peter is predicting the future. He has always been working on sequential prediction and statistical machine learning and the like, and he was always ahead of his time. And his work has influenced so many people, including myself. So I did not really prepare like a detailed CV for him. I'm not going to reveal his age or anything like that, but let me say that he has this wonderful book that's called The Minimum Description Length Principle in 2007, which was really influential. I think that was like a continuation of his PhD thesis. He's going to make some inference about those numbers if you really like. But he has received a bunch of great awards, like the Von Danzig Prize, which is like a stats and OR award in the Netherlands. It's very prestigious. He has also chaired a bunch of major conferences, including being the head of the steering committee for COLT for several years. What else can I say? Yeah, right. So he recently got an ERC advanced grant as well. So he's a rich man, but also that's like a very well-deserved award, and that is basically based on the stuff that he's about to tell us about today. And yeah, I think that's all I had to say as an introduction. So please welcome Peter.
Okay now? Okay. So let's start right away. Again, does anybody of you know who this is? Maybe if you read Cyrillic, it's actually this person, but nobody knows. Then maybe you can tell us. Yeah, this is Leonid Levin, and he is very famous for the P versus MP question, right? That's the most important unsolved question in mathematics, according to many. But he did many other things as well. In 1976, he wrote a paper which is a lot more obscure than the P versus MP paper. It's actually not even translated into English. And this is the first paper where explicitly, before that it was already in the work of Robbins, but very implicitly, the first time that something what we now call an E-value is defined as a separate mathematical object in its own right. So we come from good sources. But then not much happened with this concept, hardly anything at all until 2019. And then in the course of just 5 months, 4 breakthrough papers appeared on arXiv. So we were proudly the first one. It was safe testing, and it's now in the GRSS. And then like a month later, the paper E-values, it had E-values in the title, came. And these were actually basically the first 2 papers since 1976, which gave the concept a name. Before that, it appeared here and there, but not really with a clear name. And then there was testing by betting and a paper called universal inference. And they all have this notion of E-value as a central concept. And by now, there are literally hundreds of papers, many in these top statistics journals. And we've had 2 workshops. Next year, there will be a 3rd one. And these papers are not just about E-values and E-processes, I'll explain in a moment what they are, but also about the more general field that's emerging, and that is a field where you want to do statistics in a more flexible way. You want to have anytime valid tests and confidence intervals, which means that you can look at any time you like at the data and get something valid by looking at it, which with traditional methods is not really possible. And you can also always add new data if you like. So a lot is happening, and so this is the shameless self-promotion. You could say that there are many groups around the world now working on this, but there are kind of 2 central bases, and The most central one is at CMU, the group of Aditya Ramdas, who's writing a paper on this basically every week. And there are actually some rumors that he actually has a twin that nobody knows about because it's kind of impossible. And then a lot less papers, but still quite a lot, is my own group at CWI. But of course, we're not the only ones. And one name should definitely mention here, that's Volodya Vovk. Like Levin, he was a student of Kolmogorov, and he's basically the only one who's regularly written about this between 76 and 2019. So he deserves, I guess, most of the credit for this. So now about the talk. This is my group at CWI. I'm going to explain to you what E-values are. So the E in E-value stands for evidence. So this is a measure of evidence in data against a hypothesis. A large E-value means you have evidence that the hypothesis might be wrong. And this serves as an alternative to the ubiquitous p-value, which is still used all the time in statistics, but it also serves as kind of a bridge between frequentist and Bayesian methods, because as we will see, it has elements of both. In the end, it's frequentist. We want to get error guarantees, like probability of making a false decision is bounded by alpha, like in frequentist statistics, but we're going to use priors and other Bayesian constants, but in a somewhat different way than Bayesians do. So I'm going to explain to you first for testing, because that's kind of where it comes from, the basics. But it's very important to realize that this is not just about testing, because you basically, whenever you are interested in uncertainty quantification, things like confidence intervals, it plays a role. And we're going to get to that. But we start with testing. So the classical null hypothesis testing, that's what statisticians do all the time. And the simplest case, prototypical case, is the z-test, when you want to test whether the mean of a normal distribution has some value, usually just 0, and you assume you know the variance. So you have IID data, let's say, so they're Gaussian with some mean mu0, and your null hypothesis is that this mean is mu0, and you want to test if this is the case or not. Your alternative could be, so you have also an alternative hypothesis, and that could be the mean is anything but 0, that's one option, or you could have like a minimal effect size, saying the mean is at least this, or at most that. Everything will be covered later. And how do you do a standard test? So let's say you use this to test a new medication. So for example, you measure blood pressure of patients before and after giving the medication, and then you look at the difference. Those are your data points, so they should have mean 0 if the medication does do nothing. It's the null hypothesis. It's always the status quo, nothing special is going on. The difference between before and after treatment is 0. And the alternative is like the medication does something, so the mean is either positive or negative. Now, the way this is usually tested, that's the standard z-test, is by, you say in advance you're going to look at, let's say, 100 patients. And you fix some hypothesis level alpha, that's usually 0.05. You say significant if I get below 0.05. And then after seeing all those patients, you reject the null hypothesis, saying like, okay, I have sufficient evidence to say this null hypothesis is probably wrong. Or maybe even better to say likely to be wrong. And you do that, so the standard test you get is you do that if this happens. The average minus, let's say, 0, so that's just the average, is on the order of 1 over square root of n, where this 1.96 is what you get for alpha 0.05. If you make alpha smaller, then this value gets larger. You need to have more deviations from the null. Where does this number come from, and how does this related to p-values? Well, it's equivalent to, this test is equivalent to saying like, so I observe, let's say 1.96 over square root of n, or maybe something small, and then I look at what is the tail probability of having a more extreme outcome than what I actually observed. That's the p-value. So if you observe this, then the p-value would be this area. It's the probability of seeing something more extreme, and you reject if the probability of seeing something more extreme than you actually saw is 5%. That's equivalent to doing this, but in terms of p-values, you look at the data, you get some data, for example, here, you measure this area, that's Pn, and if that's smaller than 0.05, you reject, and otherwise you accept. So this is the standard story, but it has problems. it has many problems. A lot has been written about that. But let's look at a particular problem which often appears in practice and is directly related to e-values. So these patients, so this is not what happens here. Medical testing is not what happens in big data and AI. This is like patients are usually very expensive. You have to set up things in a nice way. So basically, often they come in sequentially. So if you could stop early, that would be very beneficial. So you test this new medication, and when you have recruited half of the patients, your boss says, maybe we should already look at the data, because if now we already have that the p-value is smaller than 0.05, we can already reject, we're done. So perhaps we can stop early. Is this okay? Anybody? This is definitely not the case. So you see, for example, that this is smaller than alpha, so you reject null, but this is totally not okay to do this. Why? Because the whole edifice, why does this method work at all? It's because it gives you something called the type 1 error guarantee. What's the type 1 error guarantee? It's the probability of saying there's an effect while there is none, of rejecting the null whereas the null is true. So that's the probability that you get a p-value smaller than alpha, even though the null is true. And the whole thing has been built to make, if you set the significance level alpha to 0.05, then the probability of a type 1 error is bounded by 0.05. That's the whole rationale behind this whole method. So sometimes you'll make a mistake. It's unavoidable. It's statistics. It's not deterministic. But you want it to be only 1 in 20 times. So everything has been set up so that if you stop at sample size 100, no matter what you see, you will make an error 5% of the times. But what happens here is that for some data you stop earlier and you reject, and for other data you go on until 100. And then the total error you make may very well actually will be larger than 5%, because on all sequences where you would reject at sample size 100, you still reject. But there are some sequences where you reject at sample size 50, but at 100 you would not reject. And now you also rejected those. So the total probability of rejection is larger than 0.05. So you violate the type 1 error guarantee. And that's the promise you made. So this is problematic because in practice people want to do this. And then classical statisticians said, yeah, but that's just cheating. It's simply, you're just not allowed to do this. But it's actually a lot worse. Because let's say we are in the same situation. Your boss says, let's look at the data. And you said, okay, well, he really wants to. I know it's wrong, but let's just do it and hope that actually the p-value will be larger than alpha so I can continue, right? And then my boss will say, okay, let's go on until 100. So let's say this happens, right? Your boss says, let's look at the data. You look at the data. The p-value was not small enough. And so you think, okay, nothing happened. We just went on. We had 100 people. Is this okay? I guess maybe you can guess the answer. This is also wrong. But now it gets really weird because nothing changed compared to the original test. And the very fact that if the data had been different than they actually were, you would have done something different than you planned to do, destroys your conclusion. Because just by the fact that this happens, you already get an error probability larger than 0.05 because the error probability is not conditional on the data, it's unconditional. So if you follow this protocol, you have more than alpha error, so it's wrong. Even if on the actual data you get, nothing happens. There are actually even much weirder examples of this. There's something called Pratt's fault meter, where you can make this as crazy as you like. And so I like to say that classical statistics is almost as spooky as quantum mechanics, because just by looking at the data, you can destroy the conclusion of your test, even if you don't act upon it. It's sufficient that for some data, not the data you've seen, you would act upon it. So people, then classical statisticians often say like, okay, let's make other procedures where you can peak because people want that, it's useful in practice, and that's what e-values give you. However, I actually like to go a step further. I'm very radical. I say, for me, this means that maybe we just shouldn't do it classically. It's just, this makes it so brittle that it depends on what happens in situations under which you have no control at all, whether your thing is valid or not. even if they don't occur, that I would just say it's a too brittle thing, maybe we should have something which is more robust in general. That's where the e-value comes in. So e-value solves this issue. And this can also be used to get real type 1 error probabilities in meta-analysis. It's super important in medical testing. Current meta-analysis, we never can give bounds on the error you make. So you put several tests together, but you know the second test has been done because the first had a certain outcome, right? Because the first was promising, you test the same medication again in another hospital, and maybe again and again. So what people now do in meta-analysis, they just put all the data together. But if you do that, you have exactly these problems. So we want a method that doesn't have these problems. So you don't have this problem with these strange counterfactuals. And another thing which it changes, which I'm not going to talk about, but which is that there's also this mysterious alpha, which is always there in classical analysis. And you have to set it beforehand. Practitioners don't get that. And when they see a very small p-value, like they had alpha 0.05, but then they see p is maybe 1 in 1,000, then they like to say, well, my alpha was also 1 in 1,000. So I can reject that I have a much better type 1 error guarantee. This is wrong, and you want to have something where you can actually allow to do that. So with e-values you are. And you can interpret in terms of bets. Again, I won't have time to go into that. So that also helps. It's easier to interpret than p-values. But of course, I'm not saying that it solves every problem, and you can hack everything, you can also hack this, and it's already happened that people used e-values in a way which is just not right. Okay, so now we get to the definition, and then I'm going to say something about how it relates to confidence intervals. So for now it's just testing, and if there's time, about composite null hypothesis, because that's where it gets really different from classical approaches. So again, we have a null hypothesis, and often also an alternative hypothesis. I gave the example of the Z-test. But another example, and this is kind of even, if you think about what's going to come up now, this is kind of better to think about this, is the t-test, which is different in one crucial respect, which is you don't know the variance. So you have something called a nuisance parameter. You somehow have to deal with it. You don't care what it is, but it's there. And if you have that, then you have a composite null, right? Because this is now a whole set of distributions, the null hypothesis, one for every variance, and that makes the whole thing, that's kind of where most of the new mathematics has happened. So E stands for evidence, but it also stands for expectation. That's how FOF got with the letter E. So here's the definition. So this is, if there's one thing you will need to remember from this talk, it's this definition. So let's say I have a sample of size n. So for now, I do assume fixed sample size. I go to this variable sample size with early stopping later on. Something is an E variable if it's a non-negative statistic or random variable function of the data, such that for every distribution in a null, its expectation is bounded by 1. And the value it takes is then the E value. So what is this? Well, the first interpretation is actually in terms of a p-value after all. If you have an e-value, then 1 over the e-value is a p-value, but it's a conservative p-value. So it gives you, it's harder to reject a null, it gives you less evidence than standard e-value, p-values. But it is formally a p-value, so this is Fisher, who liked p-values, so maybe he likes this as well. Because we know that the formal definition of a p-value is that the probability that p smaller than alpha is smaller than alpha. That's just a mathematical definition. And with strict p-values, like the one I used in the Z-test, you have an equality here. But in general, you still get type 1 error guarantees if you have inequalities. And if you have 1 over an e-value, you actually get this inequality. Yes? Yes, sure.
So a random uniform in 0, 1 is an e-value, which does not depend on data.
No, a random 0, 1 is not an e-value. Okay. Because for random 0, 1, you have to have equality here. And with the p-value, with 1 over an e-value, you usually have a strict inequality. And the strict is very important. Yeah. It's true, though, that just like you can have p-values independent of the data, you can also have e-values independent of the data. So just like with p-values, you need the concept of power to say, like, are they good or bad? With e-values, you have the same thing. So let me give you an example. The function which is constant 1 is an e-value, because its expectation is bounded by 1, but it's also independent of the data. So that's kind of, I guess that's the answer to your question. Yeah, yeah. Okay, so how do we know it's a conservative p-value because we can just use Markov's inequality. And basically it's non-negative, its expectation is small, so the probability that it's large must be small. So this means that you can do tests just like you do classical tests. Classically, you reject the null if p is smaller than alpha, or 1 over p larger than 1 over alpha. And now you reject if the e-value is larger than 1 over alpha. I always take 0.05 in this talk, so it's like you reject if it's larger than 20. So Nyman was all about the type 1 error guarantee, so maybe Nyman likes it, because you can do Nyman-Pearson tests with e-values instead of p-values. But they also have a different interpretation, namely, and this interpretation only works in this, at this level of simplicity if you have a simple null and simple alternative. So, of course, that's a kind of toy problems. Let's test if a coin is fair or whether it has bias 3/4. Then you can look at the likelihood ratio, which is, of course, non-negative. So that is like an e-value. And if you look at its expectation, you see that the expectation is the integral over the probability density of this thing. So you can write it like this. This cancels. So you get the integral over probability density, which is 1. So this thing gives you an e-value, right? Likelihood ratio is an e-value. And this is actually points to one of their main interpretations. Basically, just about every e-variable can be thought of as a huge generalization of the idea of likelihood ratio. So e-values are likelihood ratios. So now some of you might think, if you are familiar with Nyman-Pearson testing, you know that the optimal Nyman-Pearson test for testing simple null versus a simple alternative is a likelihood ratio test. You might think, hey, you just said it's different from the classical Nyman-Pearson test, which is what we saw with the z-test is 1.96 divided by square root of n. That's a classical test. So both are based on a likelihood ratio, but still they're the same because the threshold is different. If you do a Nyman-Pearson test, you reject the null if the likelihood ratio is larger than the threshold where the threshold is chosen, such that the probability of exceeding is exactly alpha. And here you reject if the threshold is larger than 1 over alpha, which is always more conservative. So they use the same statistic, but they are still different because the threshold is different. And note that the 1 over alpha threshold does not depend on the sample size, whereas the threshold in the Nyman-Pearson test will depend on your sample size. Okay, next step, we have e-variables. Now we go to the e-process. That's what happens if you have data that arrive sequentially. You can make a random process. So this is just a function of the data for every sample size. You map it to non-negative reals. And you call it an e-process if the expectation of this function is bounded by 1, not just for every fixed n, but for every stopping time. And what is a stopping time? A stopping time is, so for example, saying that if at sample size 50, the p-value is already smaller than 0.05, I stop. And otherwise, I go until 100. That is one example of a stopping time. Or if at 50 it's smaller than 0.05, I stop at 50. If at 75 it's smaller than 0.05, I stop at 75. And if at 90 I see an observation which is negative, I stop. All these things are possible as long as you only look at past data and not at future data. It's called a stopping time. Now, those of you who know random process theory will know that it's actually more subtle than that. You need a filtration to define this formally. I'm not going to do that in this talk. I'm happy to talk about it later. And so now these likelihood ratios, which you just saw are e-values, are actually also e-processes. Because, well, I don't have the mathematical tools. I didn't introduce them to do this for general continuous data, but for discrete data, you can just think of this. You have this likelihood ratio. It's defined for every n, so it gives you a process, not just for fixed n. And the expectation of the likelihood ratio for a specific stopping time is just the sum over all data at which you stop. So this could be, let's say, I sample until I see 3 ones in a row, or n is 2000. You sum over all those data, and you take the probability of that outcome times the likelihood ratio, and you can do this again, and you get 1. So you still have an variable. Sorry, you have an e variable for every stopping time, so you have an e process. And this means, and now we get back to the beginning of this talk, this means that no matter what stopping time you use, the probability under the null that you reject the null if you use this test that you reject when the E variable is larger than 1 over alpha will always be smaller than alpha. So you have to type 1 error guarantee no matter when you stop or for what reason. So you can stop as soon as the data look good. You're allowed to do that. You can look at the data. Does it look good? Yes, I stop. Your boss can tell you to stop, and you don't even need to know why the boss told you to stop. You only need to know that you stopped. You don't need to know the definition of tau, so how your boss decides how to stop. You can look at the data, anything he likes. No matter what the definition of this tau is, the probability that when you stop, you make a false decision is smaller than alpha. And this is called an anytime valid test. So now let's move to the link to Bayes. And this is just an extension for now of the link to likelihood ratios. So how do Bayesians do testing, Bayesian statisticians? Well, they also have a null and alternative, and then they put a prior distribution on the parameters in the null and the prior distribution on the alternative. So then they get marginal likelihoods. And then they take this thing, they call it the Bayes factor, and they think of this as evidence against the null. And of course, it depends on subjective inputs, namely these priors. And so note I always use this abbreviation. Why do they do this? Well, if you have a uniform prior on this and this, then by Bayes' theorem, this is just the posterior odds ratio. So it makes sense to take this as the basis of your decisions. So now what if the null hypothesis is simple? So the null hypothesis is now simple and the alternative is not. And the Bayes factor looks like this, right? Because here there's no prior anymore. There's just a point. You can put a prior on that. And now we can do the same reasoning as before. For every stopping time, this thing has expectation 1. There's just a simple null. We can just do this. So this is an E variable, no matter what prior you take for the alternative. So some priors will be much better than others, perhaps, but you always get this type 1 error guarantee. If you use this for testing, you reject if it's larger than 1 over alpha. So this is Jeffries, who came up with the modern notion of Bayes factor, so he might have liked this as well. But this is only for simple null. And this is only for testing and not for confidence intervals. And now we go into, because so for simple null and testing, this looks very much like Bayesian theory. But when we go to composite nulls and really big nulls, or we go to confidence intervals, both directions, it gets very different. And we will see why in a moment. So maybe this is a good moment for there are additional questions. No? Okay. Then I'll just go on and see. Yeah, sure. Sorry?
On the conservativeness of the E value.
Yeah.
I was wondering in simple cases how much conservatism?
I will get there. We will see in simple cases. It's actually very complicated, but in simple cases, like the normal family and the t-test, we can quantify it.
Sorry.
Yeah.
You could also adapt your examples to sequential model selection, for instance?
Mm-hmm. Yes. Yeah. So I defined e-processes, and I said, well, their motivation is that they allow you to give you an e-value at every stopping time. So no matter what the stopping time is, the probability that you reject if you use the E-best test remains smaller than 1 over alpha. But there's a kind of, it turns out in some sense even equivalent way to formulate it. If you have an e-process, then the probability that it will ever get larger than 1 over alpha remains bounded by alpha forever. It's actually quite easy to prove that once you have this, I'm always an E variable no matter what stopping time, that it implies this. So this means that with high probability, no matter how long you keep looking at the data, you will never reject if the null is true. Right? Because this is like, it will ever happen. And basically, this is actually how you prove it. This statement is equivalent to the statement if you go to a real casino with $1,000, then the probability that you will leave with $20,000 is smaller than 1 over 20. no matter how long you keep playing, and you could say like I keep playing for whatever happens first. I play for 5 years and I keep reinvesting on different roulette tables, or I hit $20,000. The probability that that will happen is actually smaller than 1/20. It's a well-known fact, and you can try it out if you don't believe it. So we know this. We have this Wills inequality. And this we can use to go to what is called an anytime valid confidence interval. So what we now do is, so I'm first going to do this for parametric models. So you have some probability model, and you want to have a confidence interval about the theta. But in a moment, we will see there are examples of theta could just be the mean of like a much wider set of problems. So theta could in general be just a general parameter. But for now, it indexes a probability distribution. Now, suppose I have an E variable, which would be an E variable is if theta would be the null. So this is my set of distributions. Let's say all normal distributions. Theta is the mean of the normal distributions. This is an E variable, which would be an E variable as that particular theta would be the null. And then I know that for this E variable, I have the probability under theta that it will ever grow larger than 20 remains bounded by 0.05. And now I define my 1 minus alpha level confidence sequence. So for every n, it gives me a confidence interval as the set of all those thetas for which this is not yet larger than 20. So these are the theta you have not been able to reject yet, in a way. You think of theta as the null, and you have some process which will grow if theta is not true. And if it's not large, then you keep theta in your set. I can't reject it, so I keep it in my set. And your confidence intervals, all theta you couldn't reject. And then by this logic, you get that for all theta at the same time, the probability that theta is not in your confidence interval at time n is smaller than alpha. But whereas for a standard confidence interval at sample size n, you only have this, now we have a much stronger result, or much stronger guarantee. It will never happen with high probability. So let's do this in practice. We have the normal location family, simple null. We've seen that, that we can make E variables by this Bayesian construction, where we put a prior on the alternative. So we put a prior, let's say, with mean 0 and variance rho on mean, and we take as our E value this Bayesian marginal likelihood thing divided by theta. Right? That's what we've seen before. This is how a Bayesian would test theta against an alternative with this prior. This is an E variable with expectation on the theta is 1. And now we take the confidence interval all theta where this is larger than alpha. Because the confidence interval is that this thing should be smaller than 1 over alpha. So that's equivalent to this thing. I flipped it to being larger than alpha. So the theta itself is not much worse yet than this Bayesian marginal distribution. And you can show that this is always wider than the Bayesian posterior interval at level alpha for the same sense. So now let me show you a graph. Or actually first. So if you take a non-informative prior, which means that you let the variance of the prior go to infinity, then the Bayesian 95% posterior interval, if you do it in a real Bayesian way with the Bayesian posterior, it becomes the same as the frequentist confidence interval, which is the 1.96 we've divided by square root of n we've seen before. If you take the prior I just showed you, you get, this becomes wider. You get a log n term. You can actually turn it into a log n term if you take a very clever prior, but I'm not going to go into that here. So let's do this because this is kind of easy to implement. You get this log n term. It's a bit wider. So here's an example. So I gave a talk for IKEA recently, and I couldn't resist. So I sample from mean 7, normal from mean 7 and variance 1. So that's the truth. I use this non-informative prior, so very high variance. And then you see the yellow is the standard Bayesian credible interval with non-informative prior. And the blue is this thing which is square root log n over n wider. So we always are a little bit more conservative. And that kind of answers your question. You have this log n factor. You can make it into log n, but then you get bad constants and so on. So this is kind of what I recommend people to use. Okay, so it's a little bit worse in that sense, but you have a much stronger guarantee because with probability 95%, the black line will forever remain in here, right? That's the always valid guarantee. Whereas for the yellow interval, you actually know by the law of the iterated logarithm, you know for sure that every now and then the true value will fall outside of the interval. That's unavoidable. But for the blue one, it will remain in there forever with high probability. That's the difference. But so now, what happens if we use a bad prior? And now we're going to see that, so we already saw that when I do confidence intervals, it's different from testing. It becomes really different from what the Bayesian does because you get wider intervals. But so now let's look at what happens if we have like a silly prior. And then we can really see very clearly what the difference is. So because these anytime valid confidence intervals, they always remain valid, even no matter what your prior is. How is that possible? Because a prior is prior knowledge. Well, it is possible in some sense. And let's see by example. So suppose we put our prior, we center it at theta is 0, and with a variance that's actually quite small. So we are reasonably sure a priori that it's near 0, but we sample like on the previous slide. We sample from mean 7. So what will happen then? And we get this picture. So the Bayesian credible interval is now very bad in the beginning because our prior was bad. It gets kind of contradicted by the data. So it tells you in the beginning, when there's not much data, that your mean is close to 0, but in reality it's close to 7. And then as you get more and more data, it slowly goes in the right way. The anytime valid confidence interval is now behaves completely differently from before. It's become a lot wider. It's correct, right? But so what happens if you put in a bad prior into a definition of an E variable, you get more uncertainty, but you don't get wrong. That's a big difference to the Bayesian approach. So E posterior gets right rather than wrong, is what I like to say. I haven't really defined what an E posterior is, so this is not a formal statement, but you can see kind of you just get more uncertainty instead of pointing you to a bad thing. Now for one parameter, this is not super important. But of course, when we use Bayesian in non-parametric settings, then we have infinitely many parameters, and how can we know our prior is anything close to being right? So I think this is kind of a good, so it's not kind of contradicting Bayes, it just says be more careful. So let me say a little bit more about it, because this is actually something I'm working on now. Because it's actually you can very clearly see that there's a very close relation. I think there's a lot more research to be done, and I invite people to collaborate with me on that. So more in general, you can define this E-based confidence set. That's basically a random function of the data which outputs a set, a subset of the parameter space, such that, so the E-based confidence set would be, you put things in the set which could not be rejected. So that the E variable is smaller than 1 over alpha. We had kind of this confidence interval I showed you was like the maximal confidence set. But this is in general confidence set. You can also make it smaller if you want. And a Bayesian credible interval based on prior W is any set depending on the data, such that no matter what data you see, conditionally on the data, the posterior probability that you're in the set is larger than 1 minus alpha. So you can rewrite this by flipping the definition of E variable as probability of theta divided by this larger probability larger than alpha, if you take an E variable based on the same prior as the Bayesian. And now if you look at not at the set A, but its complements, you can also phrase it like this. It's a valid confidence set at sample size n if this thing is larger than alpha for everything in the set. So if you're not in the set, it should be bounded by alpha. And now if you look at the Bayesian credible interval, you define it like this. You can rewrite, you can see it as the probability of not being in the set should be bounded by alpha according to your posterior. But now if you use Bayes' theorem, you can rewrite the posterior as the prior times likelihood divided by Bayes marginal. So you can also rewrite this statement as the expectation according to the prior of this thing times this is bounded by alpha. And now you see what's the difference. The Bayesian takes an expectation over the prior, so the Bayesian really believes the prior of the E variable times the indicator And the e-variable statistician thinks the maximum over all theta. Right? So this is always more conservative than this. Okay, so then, do I have a few more minutes?
Yeah, sure.
Okay. And I'll go.
I guess like
Yeah.
15.
Oh, great, I'm going faster. So maybe, again, this is a moment for questions. Yeah?
So are e-values more general than super martingales?
Yes, yes.
Which way?
Maybe reserve that question, because it's after I've shown you this, when I've shown you this, it's much easier to answer it. But for now, everything I've shown you is super martingales, definitely. There's nothing more general yet. Or let's say you can define them for each sample size condition on the past and then multiply them, and then they give you a super martingale. Product of e-values is super martingale, every super martingale's product of e-values. Yeah.
Peter, in this previous example, like, does it always make sense to be taking this maximum? I guess that depends on what you want to do with this interval.
Well, that is basically what we do now. But you could actually think of interpolating between base and e-variable based when you think like, my prior is a guess. I don't really believe it. It's just a guess. That's the e-value stance. It should work no matter what the true theta is. But maybe you do have some constraints, and then you would take a maximum not over all theta, but over a subset, or you would take the maximum over a subset of all priors, or something. So this is actually something I want to look at. So if the null is non-parametric, I'm just going to give you a very simple example there, because again, you see that you get really different methods from what's usually used in statistics. And this is the example where you only want to learn the mean of the data, and that's it. And you assume the data are IID, and let's assume, make it even simpler, the data are bounded. So now we don't make any assumptions about the data generating distribution except that it's IID. So it could be a truncated Gaussian or a mixture of Gaussian or discrete or half discrete, half continuous, anything. Anything could go, and still it's easy to make confidence intervals and even anytime valid confidence intervals. And there are basically two approaches, more or less equivalent. Gerger knows all about that. The authors do not think it's equivalent, perhaps, but everyone else thinks it is. For doing this, which just works much better than both existing Bayesian and frequentist methods for doing this. And it's based on e-variables. And in this case, you can still, I think of it in terms of super martingales as well. I'm not sure, actually. So you first look at a single outcome, and you define this function of the outcome, which has two parameters, lambda and mu. Mu is the mean. So we're going to test whether the mean is mu, and have a test for every mean mu, and by that we make a confidence interval, just like we did for the normal location family. But now the test is the mean is mu, and otherwise the distribution could be anything. So this defines our basic e-variable for one outcome. It's defined for all, so you want to test for this null hypothesis, and this is defined, it has an extra parameter defined for all lambda, for which this is always guaranteed to be positive. This is an e-variable for this null hypothesis for one outcome. Why? Because its expectation is 1 for every distribution with mean mu. Right? You don't need to know anything else about the distribution. It's just because the mean is mu, this expectation is 1. So now it starts really looking different from likelihood ratio. Now then it's easy to show that if the data is indeed IID, that this process, where you just multiply them for different data, gives you an e-process. So you can stop at any time you like, and the expectation of this thing, even if the stopping time depends on the data, is still exactly 1, actually. So we have an e-process, so now we could use this to test whether the mean is mu. However, there's still this strange parameter lambda, and it really depends. So for example, if the true mean is larger than mu, then you want to use a positive lambda, and if it's smaller than mu, a negative lambda, for example. And if it's far away, you want to use a different lambda than if it's close by. So you somehow need to find out what lambda to use to get a good test, which will give you a lot of power if the null is wrong. And so one way to do that is to learn lambda based on the data. So because at every point in time, you can basically use all the previous data This data are IID, so that doesn't depend on what happens at the endpoint in time, to estimate lambda. For example, use the lambda such that if you had used that lambda in the past, you would have had the maximal value, right? You want to use a lambda so that you reject with as high probability as possible if the alternative is true, if the null is false. So you want to use something like maximum likelihood here. And as long as it only depends on past data at each stage, it's fine. It doesn't destroy the e-value. This is still expectation 1, because the lambda does not depend on the data point on which you evaluate the e-value. You could also put a prior on lambda. So then your e-value becomes this product, because if this is an e-variable, then of course if you average it over something, an average of something with expectation 1 has expectation 1. So you can also use this thing. This is also an e-variable, and this, it turns out, you can rewrite as a product of averaged e-variables where you average according to an analog of the Bayesian posterior. So if you do this, you can have some analog of Bayes' theorem, which gives you a distribution over lambda, which gets more and more concentrated at a particular point given the past, and these turn out to be equivalent. And so you can think of this also as basically learning a lambda from the past. Now you learn a distribution over lambda, and so this works super well in practice.
This is still super hard.
Yes, yeah, I think so, yeah. And the big difference to non-parametric Bayes is that you, with non-parametric Bayes, if you want to do this, you would need to put a prior on all distributions with a given mean. That's pretty complicated, right? There's so many, and whatever you do, you always forget some, like you could use a Gaussian process or whatever. And that's why in practice this actually works a lot better. So now the composite null case, and this is basically the case where my group has done by far most of the work. This is what people in the social sciences and so on use all the time. So think of the t-test, where you want to test whether the mean is 0 or not, and you don't know the variance. And now let's again, and so now we get to differences with martingales. Let's look again at the case with fixed n. So we know that this gives you an e-variable if the null is simple, right? This is Bayesian thing divided by p0. Now, if the null is composite, this Bayes factor is not necessarily an e-variable anymore. Because an e-variable requires that for every distribution in null, this thing has to be bounded by 1. That's how you get the type 1 error guarantee, right? Because if you have this, then the probability that it's larger than 20, smaller than 1 over 20. But for Bayes factor, you don't have this. You don't have the for all. You only have this if you would first draw from your prior the parameter and then draw the data from the parameter, from the distribution with that parameter, you would get this guarantee. So it's, again, if you believe your prior, you get this guarantee, but you want it for every distribution in null. So this is not an e-variable. But now the amazing thing is that if you give me any arbitrary prior on the alternative, I can make a special prior on the null such that it does become an e-variable. So this is similar to like in objective Bayesian methods, you have these things like Jeffrey's prior, which have some min-max properties, and this is different, but it is it's a similar thing. Like you get a prior with a special property, and this is basically completely general. So in the version we had in our paper, we had to, we actually had this only for the case that the KL divergence between every distribution and known alternative is finite. And recently, some mathematical economists have actually generalized this. You can go even beyond that case. So how does it work? You take this Bayes margin on the alternative. So you give me a prior on the alternative. And now I take the distribution which is closest in terms of KL divergence. This is called the reverse information projection. Why reverse? Because you minimize in the second argument. What's called information projection in literature, you usually minimize on the first argument, and it's very different. So you pick, this is kind of I think it's called the Choquet convex hull. You basically try to find the prior, such that if you take that prior, you minimize this. So here's a picture. This is your base margin for the alternative. This is your model. And usually that model is not convex. So you have n outcomes. And now you put a prior on it. So if you look at these whole n outcomes as one unit, it becomes a convex set. If you look at this, all base marginals with all priors, it becomes a convex set, and you take the closest in the convex set. And now, so this is kind of the simplest version of our main result. If this minimum is achieved, then this gives you an E variable. So this means that if you take this prior, then for every distribution in null, its expectation is bounded by 1. And it's actually even, in some sense, the best possible E variable. In what sense? Well, if you look at all E variables, so notice that the set of all E variables also includes the function which is always 1. It's useless. You want to maximize the distribution under the alternative of the log of the E variable, and that's the one you call the best one. So why that? So we call this growth rate optimality. Others call it the expectation of the logarithm, the E power. So the idea is of an E variable is under the null it should be small. Its expectation bounded by 1. On the alternative you want it to be large. So you want to have something which maximizes this, for example, or some increasing function of this. But if you just maximize this under the alternative, then the solution has with positive probability 0. And that's something you absolutely don't want. Because you're going to use these things in a multiplicative context. If you get more data, you're going to multiply. We've seen that in previous examples. You're going to want to multiply one E variable with another. So if you get 0 for an E variable, then it remains 0 forever. So basically, you want a function here such that the solution will never give 0, will never be 0 on any outcome. And well, then there are many other reasons why the logarithm might be a good idea as well, but that's kind of one reason.
Projection done with the data, based on the data?
No, the data is not involved. I have like a batch of data, but I don't know yet what it is.
But then it's still super martingale.
No, this is now something different because this is like for a batch of data, but you can create a super martingale if you get several batches of data and multiply this. But it's on the data level, it's not a super martingale anymore. Because you cannot stop.
You're just testing to a null hypothesis.
Right?
So why is that not the same as the previous calculation?
So if you would do this for different sample sizes, in general, you get different, the prior you get depends on the sample size.
The prior depends on the sample size.
And this is basically one of our main open questions. Sometimes it does. Like in the t-test scenario, actually it does not depend, and then you get a martingale again. It doesn't depend on the sample size, but in other statistical models, it depends on the sample size. So there's something mysterious going on which we do not fully understand. Why for some statistical models, you get something which is sample size dependent, and for others you don't. But maybe we should, this is very technical, so. Yeah, another reason for taking the logarithm is that if your alternative is actually a point, then if you keep adding data, which is a natural thing to do here, that if you take the logarithm, then basically in the end it will grow the fastest. With any other function, it will grow more slowly. Yeah, that's another reason. But actually, there's a recent paper which shows that you can actually do it also with other functions than the logarithm. You get different E variables. So this is the basic theorem, but then there are other parts which basically, if this projection does not exist, it's not an element of the set of base marginal distributions, then basically you still you can still do the projection, but you get something which lies outside of the set. And in general, it's not always a probability distribution. It may be a sub-probability distribution, so it may have mass less than 1. But essentially, and so there's a recent paper by other people showing that essentially there are no regularity conditions. You can always do this projection. And there's always something which has the right properties, which gives you an E variable. So you can always get something which has this property and which maximizes this. even if this prior is not in the set of all priors. So if this distribution cannot be written as an element of what you get with the set of all priors. So a nice example is what's called the Bayesian t-test. So when Bayesians do models, hypothesis testing with the t-test, they use this Bayes factor and they do something funny. They use an improper prior. They put a prior 1 over sigma on the variance. And somehow that works. Even though 1 over sigma is not a real prior, it integrates to infinity. So in version 2 of this theorem, which is more general, which I didn't show you, that tells you how to handle some kinds of improper priors. We can show that that is actually, doing this is in some sense the optimal E variable for the t-test. Among all priors you could use, null and alternative, it maximizes this growth optimality in the worst case. And so we have a recent paper where we show that this actually, what happens here is, this is called the right-Haar prior because actually sigma gives you a scale. And you can think of what happens here in terms of group theory. You want the result of your test to be the same if you divide all outcomes by the same constant, like whether you use kilograms or pounds, it shouldn't matter, you should get the same result. And you can show that if you take these priors, you actually get that. It becomes scale invariant. And you have many other tests where you want an invariance to hold. And whenever that is the case, there exists a right-Haar prior. And the optimal E variable is given by using this right-Haar prior in both numerator and denominator. So this is what Bayesians did all along. Although they get narrow confidence intervals because they use it in a different way, but they use this prior. But in other examples, we get actually quite different priors from what Bayesians use. They're completely incomparable. And so that's kind of the main thing we're working on now is to get these anytime valid confidence sequences for linear regression and generalized linear regression. But it's a bit different from what's often done in the cold community or in the bandit community because, so we're interested in problems like this. So y is a linear function of z. There's a special variable gamma. And you want a confidence interval for gamma. So basically xe is the treatment. And these are covariates which just help you to make better predictions like, what is it, age, blood pressure, etc. So in the recent bandit literature, there are now many papers about having anytime valid confidence intervals for all parameters in a regression, right? So that if you have d parameters, you get a d-dimensional ball as your confidence interval. But here, these are kind of nuisance, just like the variance in the t-test. So you want to have a confidence interval on this, which is valid no matter what the true values of this are. And there you can use this information projection again, because now you have essentially, for every fixed gamma, you have a composite null. It's that gamma and all possible values of beta. And you take that as your null. And then by this projection, you get a very special Bayes factor, which you use as the basis of your E variable. And so we can do this for linear regression, but for generalized linear regression, it's kind of a major open problem. The theorem still works, but the projection looks very ugly, and we cannot calculate it in reasonable time. It's like n to the 5th or something if you use a trivial algorithm. And that's the whole story. So I told you what E-values are, how they allow you to do anytime valid testing, anytime valid confidence intervals, how they're different from Bayesian methods and essentially always more conservative in a parametric setting and very different in a non-parametric setting. And that's it. Thank you.
Any questions?
Okay, so I guess like one of the main points of the e-values is that they are more conservative than like what was done before.
Yeah.
But obviously, to do that you need to lose some power in the test,
Yeah.
right? Like you're going to be less likely to reject the null hypothesis. But it seems that maybe you don't lose that much, and then it's still a good thing to do. So my question is like, in a simple case, let's say you do like hypothesis testing, you have a fixed sample size, then what is like the power of the Neyman-Pearson test versus the power of the best e-value test? Like, do you have like quantifiable example in which you can see like what is the power of the best e-value test? And if that's like reasonable, like let's say, okay, I'm 5% less powerful, but then I have all these amazing properties, or like I'm half as powerful, and then maybe it's not as good, I guess.
So that's a very good question, of course. We have something like that. It's not exactly this, but almost. So we flip it around and say, suppose you have a desired power, say 0.8, assuming that the alternative is at least a certain distance from the null. So what is the sample size you need to get that power? So you say, I have a fixed sample size, I want to know what the power is, and I say, I have a fixed power, I want to know what the sample size is. So it's a very similar question. And then you see that if you look at the sample size you need with the standard Neyman-Pearson test in exponential, so this works for exponential families. I don't know if it holds more generally. It's a bit subtle, so you can look at what is your expected sample size you need if the alternative is true, because you're allowed to do optional stopping with e-values. So if you want to test at level alpha, if you want to do it aggressively, you can stop as soon as your data tells you it's larger than 20, you just stop. So you can look at the expected sample size before you can stop, and you can look at the maximum sample size you need before you are certain to have a power of, let's say, 80%. And then you find that the expected sample size is actually better than with Neyman-Pearson. Not much, but a little bit better. So if with Neyman-Pearson you need 100 data points at an alternative that's 0.2 away from the null, and beta power 0.8, you expect to need maybe 90% of the data or something, 0.9 times the sample size. But in the worst case, it's about 1.4 times the amount of data at the level 0.05. If you make the level go to 0, this alpha go to 0, it actually the numbers are always between 1 and 2. You can prove that. So you never need more than twice as many data, and for the regular alphas and betas around 1.5 times as much. You expect to need less, though. So we're in this funny situation that if everybody would adopt e-variables, the medical world would need less data than they do now, and we would save money. But no individual group has the incentive to use e-values because they have to reserve more patients. They say, okay, I might need more, right? I might need 1.5 times as much. If they do a lot of trials, then they should be able to average. So this is kind of the answer as far as we know it. So it's kind of subtle. It depends on how you define sample size.
A great answer, thanks.
All right, any more questions?
Is there any relation with another e-value which was proposed by Bayesian?
No, it's so this is a very sad thing. So the question is there a relation with that there are several other concepts also called e-variable, and one is in causal inference, and it has a lot more citations than our works. And we're really very bothered about that. We invented the name around the same time, didn't know about that work. Actually, I call it S variable. In our paper, safe testing, the S was for safe, so we were the first to give it a name. And it's like, okay, we already knew a lot of things about martingales, but we thought it's better to, if you want to make these things, it's better to focus on the increments of the martingales rather than full martingales, and we should give that a name, talk about it. We called it S variable, S for safe. Then Volodya said that makes no sense. Safe could mean anything, call it E variable. So we call it E variable, and then we just found that there are actually 3 other concepts called E variable. But it's too late, I think, to change now because there are too many papers, so it's a problem, and I don't know what to do with it. It's definitely not the same. There's no relation at all, actually.
So there are multiple E communities.
Yes, yes. And you get these papers where they said, well, the E variable is very bad, and then they don't talk about us. Yeah.
Okay, maybe I'm going to make a fool of myself, but if you take the E process and then redefine a minimum at time n, minimum over all the past SI, don't I get a super martingale in that case? Super martingale, which is even better than the
yeah. It's not exactly like that, but it's similar. So, okay, so the way it works is that, and that's the reason why we talk about E processes and not super martingales. If you have a simple null, they're actually the same concept. For every super martingale can be written as a product of E variables for the ith data point, and every product of E variables gives you a super martingale. Now, if you have a composite null, it's not the same anymore.
But from the definition, if you define E values the way you define, and you take the minimum over the past values, then it becomes a super martingale.
Okay, in the way I define it here, yes. That's the answer is yes.
So then there is always a better super martingale than the E value that you define. So you can improve your bounds. Okay, maybe I'm making a fool.
No, so the first thing you say is correct. And actually that's kind of what happens in this universal inference paper. But the second thing is, why would it be better?
Because you take a minimum over the past.
Yeah, but you want to maximize it, right? So the thing is, you want the thing that under the null it should be, under the null it has to be small, but on you want something which under the alternative is maximal, or its expectation is large, because you want to have power. You want to have something which allows you to reject. So it's kind of a constraint optimization. You want expectation bounded by 1 on the null, and then under the alternative it should in some sense be large. And if you take the minimum, which is actually what people have done, so in practice often you can do something more clever to make a martingale, because this is like being very aggressive in a way. The minimum will always work, but you lose a lot. There might be actually much better martingales. Well, there are lots of papers about that. But basically, the answer to your question is yes, this does give you a martingale, so you can always make one. It's just often not the best one. Because best is defined in terms of the alternative and not the. No, yeah. So maybe I should say one final thing briefly, as I forgot. So there's one thing I didn't talk about, and this is also like, if you like, isn't this the same as martingale theory if you ask that question? So I mostly talked in the sequential setup and with optional stopping, and then you get something very closely related to martingale theory. But this is also used in multiple testing, and there they look at like single batch of data, and they don't vary time, but they vary the hypothesis they look around. And then you want to have like optimal E variables for that, and then you only care about the specific sample size. Expectation should be bound by 1 for that sample size, and then kind of the connection to martingales breaks. You have like the E variable, you have E variables but not E processes. E processes are just almost the same as martingales, just so that people know. And there's also lots of papers about this using in multiple testing, but I haven't worked on that myself.
Maybe I can just ask one last thing, because
Sure.
I'm really curious about what you said about e-hacking. So what are some examples? Because it looks like, this is like an invulnerable concept.
Yeah.
Works for everything, but still, how can you break it?
Well, you can do optional stopping, right? But what you cannot do is optional starting. And people have done that. So they've said like, well, the first 25 data points didn't look so nice yet. So we start at sample size 25. And then we stop, and then it looked good for a while. And so we take this interval. That's the first, the first known instance of e-hacking. That's not allowed. You can, of course, kind of make something where you can do that, but you have to be a bit more conservative again. But if you do the standard thing, there's no, you lose the guarantees if you do this. Yeah. So this is, yeah.
Okay. That's something that I would have never thought about by myself.
Yeah, but that's the thing. It's like there's a famous quote from some, like you can do things right in only one way, but there are like infinitely many ways in which, so you can never think of what people come up with. It's, yeah.
All right, sounds like we got like a lot of homework to do to come up with ways of breaking Peter's theory.
Okay, great.
All right, let's all try that, or maybe try to use it correctly. All right, thank you, Peter.
Okay, you're welcome.